Everyone, I'm just setting the YouTube Zoom live stream. It's loading. Live stream. It's loading. All right, so we're live there. All right. Well, hello everyone. Thank you very much for joining this month's EPSP Connects. Just a reminder, the whole idea behind this series is to bring the community together, help establish connections between people who might not be able to interact with others in a different setting. So we're very happy to have you here. I'd like to thank all the EPSP Connects team members who helped plan, organize this series, reach out to potential speakers, panelists, coordinate with them, and who advertise on social media, make sure this series is running as good as it does. Joining me today as co-host is Alvise Finotello, who will help us with the Q&A. Alvise?
Hello, everyone. Welcome from my side too, and please use the chat to post your question. Roberto and I will keep an eye on them. And for those viewing our live stream on YouTube, we will also keep an eye on it for questions. So please post your question there as well as they come up.
So we have two speakers today, Dr. Dan Scott and Dr. Charlie Shobe. Dr. Scott is a fluvial geomorphologist who studies how rivers shape and are shaped by landscapes and living things. He seems to wear three different hats as a co-owner of Riverscape Science and Stewardship, senior geomorphologist for watershed science and engineering, and research scientist at Colorado State University. Dr. Shobe, is that how you pronounce it? Shobe? Okay. Is also a geomorphologist. His work integrates numerical models and field data to understand processes that shape rivers and watersheds, especially as they respond to environmental and human-driven changes. Dr. Shobe is a research geomorphologist at the U.S. Forest Service Rocky Mountain Research Station in Fort Collins. So with that, Dr. Scott, Dr. Shobe, the floor is yours. Please take it away.
All right, thank you so much, Roberto. It's good to see everyone. Today we're going to be talking to you about channel adjustment and especially avulsion in gravel bed rivers. Oh, sorry, let me get my presentation started here. All right, so Charlie's going to talk a little bit more about numerical modeling and kind of the channel adjustment side of that title. I'm going to present on a field study of bifurcations, really channel splits. That's essentially what a bifurcation is. And avulsion, the key process that regulates these channel splits, that forms them, that maintains them over time, and that reshapes the valley bottom of multi-thread river systems. I want to both introduce some terms here to make sure we're all on the same page, but also give us some motivation for thinking about split channels or bifurcated channels. The way I think about it, split channels or splitting channels really makes our life easier, and not just our lives as humans, but also the lives of fish, riparian vegetation, beavers, really any animal or plant life that I can think of that likes to live around a river seems to like split rivers a little bit better. They seem to like multi-thread rivers, rivers where not all of the flow is going down a single channel, where we have smaller side channels, where we can turn big rivers essentially into a bunch of small rivers. And on the human side, you might be kind of doubting me, especially if you're maybe a civil engineer thinking about building bridges. I will admit split rivers are wider and harder to cross, but they dissipate energy a lot better. They tend to be easier to build infrastructure along, and they tend to be easier for us to interact with and to manage. Quite simply, they have less concentrated energy, and that's just easier for us to deal with. If we want to manage and better understand these rivers, what I will argue is that we really need to understand how they adjust over time. And the main process by which these multi-thread rivers adjust is the process of avulsion. I'm going to define that here as the redistribution of flow between channels. That is a very holistic definition of avulsion. That means that avulsions can progress slowly, they can progress quickly, they can progress fully or partially. And I'll use those terms and kind of define them throughout this talk. I want to start by showing you just an example of what I mean by a dynamic bifurcation in an anastomosing river. This is the Tolt River in Washington State, USA. I'm going to show you some historical imagery from 1977 through 2009, just to kind of get us on the same page about what avulsions can be. So you might notice that here, a lot of the flow, if you can see my cursor, is going down this left channel with this arrow here kind of representing that. Skip forward a decade and oh boy, an avulsion's happening. This is getting exciting. A lot of flow is going down this right channel, but yeah, we still got a fair bit of flow going down the left one. Skip forward yet another decade and oh gosh, it looks like that left channel's closing off. Looks like this thing might revert back to being closer to being a single thread river. It's kind of a bummer for all these fish. But no, actually the avulsion changes direction. We skip forward another decade and we see that this avulsion that was trending towards this right channel is now again trending towards the left. It's done so relatively slowly, or maybe you could think of it as more of a stepwise thing that happens in spurts. And to illustrate one of those little spurts, we see just in the course of a single flood, over the course of a few hours actually, this river transitioned from being a nice, almost 50-50 split to almost all of the flow going down this left channel, just like it was back in the 70s. So what I want to illustrate here is that avulsions can progress fast or slow, but they are often complicated. If you can glean just from this historical imagery how this system is working, that's amazing. I first saw this and I could not do that. I've been studying this system and many others like it really for the past, gosh, I don't know, 7-8 years, and I'm still having a hard time wrapping my head around them. What I want to do today is present some progress that we have made in terms of understanding these avulsions, not just to help us manage and interact with these rivers. You may notice there are people in this floodplain. There are fish and beavers that live in this valley bottom that we would like to help out. So not only for the management side, but really I would make a case that in these anastomosing rivers, these rivers that have space to rework their valley bottoms, avulsion is the key process that regulates that valley bottom template. It regulates the riparian forest. It regulates patchiness. It regulates where the channel is going to migrate, where fish can live, where biota can influence this system. It is a fundamental driver of these multi-thread riverscapes. If we want to better interact with these riverscapes and maybe even steward them, we need to be able to answer two key questions. The first is, what regulates the relative size of one channel versus another? Why is this channel so small and this channel so big? Simple question, right? Second question is, what regulates avulsion progression? You may have thought that I was going to show you a meander cutoff here. I just skipped forward about 10 years. No. And if you thought that this channel was going to cut off, well, that illustrates why we need to understand these systems. We are taught that water tends to follow the path of steepest descent. As I'm going to show you today, that's not really true, especially around channel bifurcations. Where flow splits, water does not follow the path of steepest descent, arguably in most cases, which is pretty mind-blowing to me, and in my mind motivates study of these dynamics. So I'm going to go over some of the work that folks have done to better understand these systems, starting with kind of a timeline of how we have conceptualized and understood avulsion dynamics. So throughout a lot of the 20th century, our conception of these systems was really focused on slope, was really focused on this idea of water following the path of steepest descent. There were a lot of seminal papers that essentially argued that when all else is equal, avulsions will happen when one channel has a much higher slope than the other. As I illustrated here, though, that's not always the case. And actually, if we start looking through empirical data sets, especially large empirical data sets of bifurcated rivers, we find that in most cases, all else is not equal. Essentially, slope is not the driving factor in these systems. From the kind of 1980s through the 2010s, we started to build a more concrete picture of how wood regulates these systems. And it became very clear that wood can be one of these key factors that kind of breaks the influence of slope. It can force water to follow a flow path that is not the one of steepest descent. It can force an avulsion, essentially. And that makes sense. You would think that, yeah, if there are two channels and you dam one up, the water is going to go down the other one. Sure. But as it turns out, through the 2010s, we've made some great progress, mainly through numerical modeling, in terms of figuring out how hydraulics really work in these bifurcated channel systems. And I'm going to summarize all of that. It is very complicated, but I'm going to summarize all of that complex hydraulics with a term called incidence angle. And even that is still kind of complicated, so I'm going to simplify that even more to say that incidence angle essentially means how much water has to turn. If you didn't know, water is very heavy and it can move very fast, and it's very hard to quickly turn very fast moving heavy things. So we describe that with incidence angle, illustrated here on the left with a high incidence angle. Basically, water has to take a very sharp turn to get into this channel, and water doesn't have to take a sharp turn to get into this channel. Numerical modeling shows us that flow will generally follow the path where its momentum kind of drives it. This is an illustration of that around an outer bend showing velocity or modeled velocity, where you have two channels, one that is much steeper than the one on the top, but the one on the top is more favored in terms of really secondary flow patterns, which we can summarize or proxy with incidence angle. Again, this is a gross simplification of some very complicated hydraulics here. So we've learned that a lot of things can kind of overpower slope in terms of determining how an avulsion will progress. And I would say that our current state of the science is that we are wrestling with a lot of complicated driving and resisting factors that can regulate avulsions. We're starting to come up with more holistic conceptual models, but we cannot yet integrate all of these variables that we know may influence channel adjustment in bifurcated channel systems. And I'm actually going to go ahead and complicate this even more. I work in the field a lot and I help people manage bifurcated rivers. And I've noticed there are just a bunch of things that we have not yet addressed in the literature. Things like distributed roughness, not just wood at a channel inlet, but wood all the way down one of these split channels. Or what about other sources of roughness? Vegetation. What if we throw in beavers to this mix? And for all the roughness we can give these channels, what if they can just erode around it via incision of their bed or migration, bank erosion? What about compound bifurcations that I've illustrated here, where rivers split and then split and split and split before coming back together? How do these function? And most importantly, when we're looking at real river systems, if you recall back to those papers in the 20th century that thought slope was the driving factor here, but we really have found that that was only true when all else is equal. Well, that's real river systems for you. That's gravel bed rivers. What about when all of these factors interact? So that's what Charlie and I are working on. My side of this is, and what I'm going to talk through here is an empirical study of avulsion dynamics and the behavior of bifurcated channel systems. We're tackling this in a two-pronged approach with this large empirical study paired with numerical modeling, which is going to be the second half of this talk that Charlie's going to go over. This empirical study, I've been conducting it in two ways. So one, doing some historical analysis of bifurcations over many decades. And then two, I have this ongoing work trying to do field surveys of bifurcation dynamics, where we're actually measuring every little thing about these channels and the bifurcation itself in gory detail, and we are trying to understand how they evolve over time. Really focused on these same two questions that I highlighted earlier. Why are some channels big and some channels small? And what regulates the progression, or especially the direction of avulsion? I'm going to actually skip through a lot of this data. I can come back to this if folks have questions. I wish I had time to go through all this. The statistics are so interesting when you're dealing with paired channel systems. If you want to talk to me about that, I would love to, so reach out. But I'm going to try to summarize a lot of this empirical data set for you. First, focusing on that question of what controls relative channel size. And I'm going to both illustrate this with this image on the right. This is an aerial image, again from the Tolt River, one of my favorite rivers. And then a list of kind of what things are, what is emerging from this data set. So thinking about what makes some channels big and what makes some channels small, well, we've found that, as we would expect from the literature, a low incidence angle, essentially not asking the water to turn very sharply, and having less wood blockage at the inlet, something like this, so not having this, allows a channel to get large. That makes sense, right? I would really hope that we would find that, but it is important to document findings in large empirical data sets. We've also been able to add some really important things to this list of variables that control avulsion and bifurcation dynamics. Those are flow concentration and distributed roughness down the length of each of these channels. What I mean by flow concentration is essentially just flow width. It's a little more complicated than that, but if you think about it, you can boil down sediment transport capacity, or really the continuity of sediment transport capacity, to a question of width or unit stream power. As illustrated by this channel here on the left, this shorter, but as shown here, much steeper channel, as soon as water goes into this inlet, it spreads out by a factor of somewhere between 3 and 5, depending on the year. That spreading out basically dissipates energy. It makes it really hard for this channel to continuously transport sediment. It makes it very hard for a head cut to propagate up through this channel. That compounds the effects of this large wood jam at the inlet and an incidence angle that is slightly less than the channel on the right. We've also found that roughness, especially in the form of very dense accumulations, things like wood jams or beaver dams, those can very strongly influence essentially the ability of these smaller channels to widen and enlarge, to experience an avulsion, essentially. They can resist an avulsion, and I'll speak more on that later. I'm going to kind of rank this evidence to give you a sense. As I mentioned before, we're very much in the midst of understanding avulsion dynamics. And I would say that what I'm telling you here, there's moderate to strong evidence of this in this empirical data set we have, but there are good indications that there is a lot more to this story. Things like bed and bank erodibility. Those seem to be emerging from this data set, but I'm not confident enough to really tell you that those are driving factors in a lot of avulsions. So stay tuned. It might take me another 10 years, but we're going to figure this out. Heck, might take me the rest of my career, now that I think about it. All right, I'm going to move on to the second question. What controls avulsion direction? Again, I'm showing data here that I'm not going to go over. I'm sorry. I'm going to try to just illustrate this and sum it up in one sentence that has a lot of information in it. So I'm going to take this slow. Avulsions progress in a time-lagged manner, so they lag behind their influencing variables or their driving variables, in a direction that follows changes in things like incidence angle and wood blockage at the inlet. So essentially, these things that regulate how much flow can get into one channel or another. I've illustrated that here. This is that same progression of historical imagery that I started the talk with. And you can see that as this blue arrow indicates, this is upstream flow direction. As this floodplain erodes, this orange patch of floodplain, which you'll notice is not here in the latter image, as that erodes, the direction of avulsion followed that change in incidence angle. But it did it in a very time-lagged manner, like following 10 years or more behind that. That's really cool to me. Not only does it imply that we can actually predict changes in the direction of avulsion, but it implies that these changes will manifest, or signs of these changes will manifest before the avulsion actually progresses. That's the time-lagged manner, and that means we can actually predict these things. We can go look at rivers and say, yeah, actually, I think that channel is going to start experiencing avulsion in the future. I would say that there is a lot more to this story. This is a key target of our field investigation. We are tracking avulsions as they happen over time during floods. We also need to start tackling the problem of avulsion rate. As I mentioned, avulsions can range from slow to fast, and we have barely started making progress on that front, but we're getting there. So there's a lot more to this story. For now, I'm going to summarize this in a conceptual model that describes essentially where we can get, or how we can get multi-threaded systems that are driven by partial avulsion. This conceptual model space has two axes. On the y-axis are what I'm terming flow diversion drivers, essentially the factors that regulate how much flow is getting pushed into one channel versus another around a bifurcation. Those are things like wood blockage and incidence angle. And again, there may be more things here. Again, check back in 5 or 10 years, and this list might be longer. But they all regulate essentially how much water is making it into the inlet of these channels. On the x-axis here are avulsion resistors, basically things that operate downstream of the inlet, that mess around with all that water once it enters one channel or another. Those things are distributed roughness down each channel and flow concentration, basically whether the channel spreads out or maintains a consistent width. And this is a little counterintuitive, but avulsion resistance is high on the left and low on the right. So if we have low avulsion resistance and high flow diversion from one channel to another, that's where we get full avulsions. Basically, we're pushing a lot of flow out of one channel and into another, and that other secondary channel has no capacity to resist avulsion, so it captures the entirety of the main stem. Where we may want to be, if we want to steward multi-thread rivers, is more in this middle ground, where we have some flow diversion out of a main stem channel, but enough resistance to keep that new channel from experiencing a full avulsion. I'm going to illustrate how we can use this conceptual model. A lot of my kind of day job as a consultant is people asking me that they want to get a side channel for their fish for Christmas, more or less. We want to build side channels for fish. I work a lot in the Pacific Northwest, and that's a large part of what we do. We can actually use this conceptual model to help us kind of parameterize this problem, to understand what variables we should be looking at least on the local scale. We can look at different side channels and we can say, well, what are the differences in their incidence angle? And how might that change the amount of flow getting into them? What are the differences in how they will resist avulsion? So A and B here go through a forest. That's great. That tends to concentrate flow. That can be good in terms of sustaining side channel connectivity. C here, it has a slope advantage, but remember, slope is rarely the thing driving these systems. C actually flows through a farm field. What do farm fields do? They allow flow to spread out. They don't keep flow that would go into the overbank neatly squared away in the channel. They allow energy to dissipate. And so we would say for C here, this might actually, if we were to, let's say, dig a side channel through here for our fish, that might just close off. So what I'm hopefully illustrating here is that we might not know all of the factors that regulate avulsion, but we can start to put those into this conceptual model of flow diversion drivers and avulsion resistors and start to conceptualize this space in terms of what is driving how much water is getting into these channels and what is resisting their expansion. If we do that, we can hopefully understand how these will behave over time. I want to emphasize, though, in this slide, that these local factors I'm talking about integrally depend on watershed scale processes, the regimes of flow, sediment, and wood. And I'm going to finish with this example, which I think really neatly illustrates this. This is two bifurcations that have almost identical geometry. One is a little bit larger than the other, but there's a key difference between these two. This one receives almost no wood supply from upstream, and that basically deprived it of those factors that provide avulsion resistance. That allowed this avulsion during a flood in December 2025 to fully progress. It allowed the main stem to essentially switch from over here to over here. That just maintains a single thread channel. That's kind of a bummer for fish. This one down here received a lot of wood from bank erosion and channel widening in here. And yes, that is a tree going through someone's house. That's very unfortunate. Unrelated to the avulsion dynamics, I think, I hope. But this avulsion, the key difference here is that it had a lot of wood supplied to it. Coming in from upstream, that wood allowed it to resist a full avulsion and maintain a channel split and maintain a multi-threaded planform in this area. So with that, I would like to thank a lot of people who have contributed to this over the years and also turn it over to Charlie, who will take it away with some information about numerical modeling. Thank you.
All right. While I share here, I'll just note we are going to do questions at the end. So save them up, put them in the chat, whatever you want. I'm going to share this, and then I'm going to do the slideshow. Okay, so you all are seeing just the slides, right? Okay, that's good. Sometimes my notes can be a little snarky. Okay, perfect. So thank you, Dan, so much. My name is Charlie Shobe. I'm a research geomorphologist with the U.S. Forest Service Rocky Mountain Research Station. And I'd like to pick up right where Dan left off, thinking about this comparison of a wood-rich and wood-poor pair of channels on the left side or downstream side and right or upstream side of your screen, respectively. And the idea here, like Dan said, is that this wood accumulation you see on the left pair might have played a role in influencing avulsion dynamics and ultimately driving a different outcome from the pair on the right. And I'd like to use this specific example to zoom out a bit to focus on the general case of roughness in river corridors. Wood is something we talk a lot about. We see a lot in rivers, especially in the Pacific Northwest. But it is just a general or a specific example of macro roughness, right? Which can come in many forms. And by macro roughness, all I mean for the purposes of this talk is large obstacles that obstruct a river's flow. And these come in all kinds of shapes and sizes. So we can think about root wads on the top left, tree trunks on the top right, low-tech process-based restoration structures like in panel C here. This is in Colorado and is an example of an attempt to slow flow and send it over bank by adding roughness to a channel, as well as boulders, my personal favorite roughness elements, which you can see in panel D here. Regardless of the source of macro roughness, what we're interested in is the mechanics by which it influences channel dynamics. Oh, I'm sorry. There are also lots of types of roughness I haven't pictured. Landslide deposits, beaver dams, rigid vegetation, human-built things like bridge piers or whitewater parks, all kinds of stuff. And what we're interested in is how that roughness influences channel thread dynamics and ultimately scales up to influence the form and evolution of multi-channel riverscapes. So I want to focus today on two questions, both dealing with how roughness affects individual channel threads, and then I'll hope to sort of draw some implications for the evolution of multi-channel river systems. So first, I'm going to think about how macro roughness influences the equilibrium or steady state geometry of individual channel threads. And then we'll look at the transient problem or ask how channel threads respond to abrupt changes in macro roughness. And this is probably the more relevant question to thinking about kind of abrupt environmental changes to river channels. I've got a nice example here from Julie Scamardo, who recently published on a big forest blowdown event. So on the left-hand side, you see all these trees that have been blown down by wind. And on the right-hand side, you see a tiny little stream channel that's totally choked up with trees and root wads. And this also is really relevant for studying river response to human interventions. And in particular, I would point out that right now is kind of a nice time for fluvial geomorphologists to be working on these problems because process-based restoration, like that picture here from Colorado, is proliferating, but not a whole lot is known about best practices or what might be expected to happen as a result in any given system. So lots of interesting implications here. And we're going to do this for my part of the talk through the lens of simplified numerical modeling of stream hydraulics and morphodynamics. So I'm going to take a second to kind of set this up and explain what we're doing. We're going to have a model domain that I've sketched out on the left-hand side here. You can ignore all the variable names that you can think of as a channel cross-section that extends a number of channel widths in the upstream to downstream direction. And the reason we do that is to keep this model as simple as possible. The model is actually zero-dimensional, so we're not explicitly evolving the channel along either a longitudinal or cross-stream coordinate, but we're simply evolving the channel bed and banks along a patch of channel that extends up or downstream. And I also want to emphasize that this represents not a single roughness element, right? It's not modeled response to one beaver dam or whatever. It's the response of a channel reach that contains a series of roughness elements. And the reason for this is that the channel reach needs to be long enough that we can think of one-dimensional flow as steady and uniform with applicable common flow resistance relationships. So the way we account for macro roughness effects, and this could be logs or boulders as I've drawn in on the left-hand side, is by using the reduced or effective energy slope approach of Rickenmann and others, where we basically calculate how much energy is lost to drag on these macro roughness elements and reduce the effective energy slope of the flow accordingly. So if there's a lot of roughness, you have less energy remaining to do sediment transport and erode the bed. And we also account for bed and bank cover. These obstacles might block off part of the bank, right? Sometimes in restoration, that's the point, and prevent erosion of certain parts of the channel. We move sediment with standard bedload transport approaches, and then we evolve the channel geometry under a transport limited assumption. So the idea here is that there is always sediment available to be moved if there is sufficient shear stress to move it. And the channel can evolve its width, it can evolve its bed elevation, but it will always remain a trapezoid. Okay, so that gets that out of the way. Let's dive into the interesting stuff. How does the addition of macro roughness influence equilibrium or steady state channel geometry? I'm first going to show you this plot, which is representative of a bunch of plots you're about to see. So I'm just going to take a second and explain it before we dive into the results. So on the x-axis, which is logarithmic, You're looking at the roughness length scale that defines how rough the channel boundary is. That's something we set in the model. And it ranges here from about a centimeter roughness length scale to about a decameter. And the reason we chose those limits is that that results in our model covering about the entire range of relative submergence values that are observed in common hydraulic data set compilations like those by Eric Deal or Rob Ferguson and others. And then on the y-axis, we're going to plot some morphologic response quantity, in this case width, and we're normalizing to that bottom left point, to the low roughness end member. And I do that to keep everything at kind of a higher abstract level and not get bogged down in exact values. And so numbers greater than 1 on the y-axis tell us that channel width is increased as a result of increased roughness, and numbers less than 1 would indicate a decrease. What we find when we look at channel width as a function of roughness is that roughening widens channels while the channel is adjusting its form to keep the bed and bank shear stresses constant or near critical across the whole range of tested roughness length scales. And so I'll sort of diagram along the bottom here the mechanics of what's happening. If we start with some channel that we place roughness into, that roughness causes flow resistance, which reduces flow velocity and increases depth. That reduces the width to depth ratio, which disproportionately increases shear stresses on the banks. Bank shear stresses are very sensitive to that ratio. And then the channel banks widen to the point where that stress re-equilibrates, right? Or where the channel can no longer widen. So the width response, reasonably predictable. Channels seem to widen predictably as a function of imposed roughness. The response of the channel bed is a little more complicated and interesting. The response of the channel bed depends on how much roughness is added, and we can spell out a few different regimes of behavior here. So what I'm plotting on the lower plot is channel local slope, right, which is directly tied to the state of the bed in the sense that aggradation steepens the local slope and degradation reduces the local slope. In the purple squares, I'm showing you bed slope, which is exactly what it says. And in the pink triangles, I'm showing you that energy slope, which will always be less than the bed slope and is progressively reduced as roughness gets greater and greater. So what we see here, when we start over on the left side of this slope plot on the bottom, is that there's a large regime of roughness increases for which there's little to no slope response. So why is that? What we see in this regime is that there's initially increased flow depth due to roughening, but the response is dominated by widening, by increasing bank shear stresses that widen the channel until it re-equilibrates. And that's accompanied by only very minor bed incision because there hasn't been a significant increase in bed shear stresses. Most of that energy is being used to widen the channel. Then we've got this regime in the middle here, 3 points in the middle, where we do see the local slope or the bed start to really respond. And that's happening because we see increases in flow depth coupled with greater reductions in energy slope due to roughness becoming more dominant. And so that's where we see this coupled widening and aggradation or steepening regime in which the channel needs to both widen and steepen to enable it to reach equilibrium, right? To transport sediment out of the reach at the rate that it's being supplied. And then finally, on the right-hand side, we've got these points that I've rendered as translucent. So you might ask first, why did I do that? And second, what's going on in that regime on the right-hand side of the plot? So I'm going to diagram this out in little sketches on the right-hand side of the slide here. So this regime where I've plotted translucent points actually represents an unstable end member of runaway aggradation and channel filling. And I think this makes a really interesting tie-in with the sort of avulsion and multi-channel riverscape story, because channel filling of one channel thread is typically tied to initiation of a new flow path, right? So what happens here is that the roughness forcing is so great that you add a roughness to the channel and you start forcing the deposition of sediment, the rapid deposition of sediment. And I'm rendering that in yellow, that's filling in the bed there. That deposition is really rapid because roughness has caused such an increase in flow depth that flow is starting to spill over bank. And assuming you're in a wide floodplain, you lose that flow. It's not contributing to depth in the channel, and it's not contributing to shear stresses along the bed. So you see extremely rapid deposition. That deposition raises the bed elevation, further reducing your conveyance capacity for water, which sends progressively more of the flow over bank, and you have more of a lack of shear stress to erode the bed. And this process continues until the channel has filled. So this is sort of equilibrium in the sense that the process has an end. But in nature, this would be accompanied basically by that overbank flow finding a new flow path or activating a new channel across the floodplain and causing an avulsion. And so what the translucent points in the plot are showing you is the geometry that we would obtain for an equilibrium solution if we simply didn't allow flow over bank, if we assume the channel banks were always deep enough to contain all of the flow. That's not really realistic. Gravel bed rivers, unless they're in a canyon or something, tend to be accompanied by sufficiently wide floodplains that this overbank flow deposition feedback is probably a realistic set of outcomes. So we asked initially how macro roughness influences the equilibrium geometry of channel threads. And what we find is that there exist three regimes of equilibrium channel form in roughened channels. One starting from the left that I've called the widening dominated regime, a middle regime I've called the widening and steepening regime, and finally that filling regime on the right-hand side. And one thing I want to take a second to emphasize here is that these regime boundaries and the exact position of these data points, all of that will shift under different model parameterizations, right? This is a numerical model. We impose things like the discharge and the sediment flux in. And so I don't want to leave anyone with the impression that this is what will happen at your field site. Just that this represents the broad envelope of possibilities over the sort of full range of naturally plausible roughness states of gravel bed rivers. So for the last few minutes here, I'd like to move on and think about how channel threads respond to abrupt changes in macro roughness. So this is effectively looking more closely at the transient part of the problem. So the plots I'm going to show you now, starting with these, are a little simpler to understand because they're over time. It's normalized time, but I've got the sort of representative time scales labeled in the plots I'm showing you here. So the way this works is that all of the left-hand months plot fits in just the first little bit of the years to decades plot, and so on. And so these are sort of nesting dolls of plots moving from left to right. And on the y-axis, you're always going to have normalized morphologic quantities, in this case, starting with channel width. So this is showing us maybe something we're a little more directly interested in, which is if we make some major change to a gravel bed river channel, how is any particular facet of its morphology going to adjust over time? And what will we observe when we go out there to make measurements? And the different colors here are showing you different degrees of roughening, right? So the dark colors show relatively small increases in macro roughness, and all the way up to the green and yellow colors showing you major increases in macro roughness. And so what we see when we look at channel width over time in channels that have experienced a roughness perturbation is that channel width basically increases more or less monotonically with time and with the scale of the roughness perturbation. So the longer you sort of wait to go look, the more the channel will have widened, and the greater that response will be. That response will also be greater the more the roughness state of the channel has been perturbed, the more boulders you've added, or the bigger the beaver dam was built, or whatever. Things are, again, a little more complicated when we think about the state of the channel bed or the local slope, one of the other key morphologic variables that we tend to measure as an outcome of changes to river channels. So 2 points to make about this here. One is that the initial direction of change, which is to say whether your channel slope initially declines or increases, depends on the scale of the roughness forcing itself. So that's most easily seen on the left-hand side plot here, first few months of evolution, where if you have a relatively modest perturbation to the state of macro roughness, we actually observe that channel slope will have an initial decline before beginning to recover. Whereas if you really crank the roughness up, you can see nothing but increases in channel slope. The other thing I want to really emphasize here is that the sign of the change, which is to say whether you are above or below 1 or your pre-existing channel slope, is a function of time. And this is maybe best seen in the middle plot labeled years to decades there, where we have a number of lines that cross 1, which is to say that the slope might initially decrease for a while, a couple of months or a couple of years, relative to the pre-roughened state, but then the line will cross that 1 threshold, which is to say the slope will then be greater than it was before the roughening. And the reason I'm belaboring this is because often we want to go out and we want to measure channel response to some natural or human perturbation. And what this means is that some of the morphologic responses not only depend on the scale of the perturbation, which sort of makes sense, but depend on when you decide to go out and measure. And this is important because often our measurement campaigns are either very detailed or longer lasting, but they're not typically both. And so this is important to consider when planning those sorts of efforts and when sort of conceptualizing the results that we might or might not be seeing when we make those types of measurements. I think the best way to explain this complex bed state or local slope response is by looking at the shear stresses on the bed and the channel bank. The reason that the channel width response is relatively simple, but the slope response is variable, is because bed stress can initially either increase or decrease depending on the roughness forcing. And what I mean by that is if we look at this upper plot, we see some lines that start above 1, meaning you have an initially greater bed shear stress due to added roughness than you did before, and some lines that are less than 1, where you have an initially less bed shear stress than you did before. Whereas bank shear stresses always increase as a function of roughening because you always have roughness driving increased flow depth, reducing the width to depth ratio, and increasing the stress on those channel banks. So this ultimately all comes back to the partitioning of fluid stresses between the bed and banks that drives a relatively consistent and predictable width response, but a relatively complex and time-varying slope or bed response. So we asked how channel threads respond to abrupt changes in macro roughness. And in general, the points I want to leave you with here are that transient width adjustment is largely self-similar. Initial slope change, though, depends on the roughness perturbation, and the responses of local slope or bed topography vary based on when you look. And to extend to the sort of avulsion and multi-thread channel problem, because individual channel thread slope dynamics play such an important role, this also means that these changes may propagate through to looking at differences in, say, channel thread dominance over time. So 2 of many I could have put major caveats to keep in mind here. First, the equilibrium times we simulate are probably long relative to the persistence of many particular types of roughness, right? A particular log jam or a restoration structure, some of which are not intended to last more than a couple of years. So really in nature, probably a lot of these systems are a number of stacked transient responses. Second, we haven't really examined these interesting and previously identified feedbacks between roughness and channel geometry, such as bank widening, recruiting trees into the channel, and thereby leading to more roughness and so on. So a lot to explore there. And finally, in the next few months here, it is our hope that Dan and I will be using this model to sort of explore Dan's conceptual space by using modeled pairs of channels to quantify the interactions that affect multi-channel riverscapes. Thank you very much.
All right. Thank you both for, I guess, an excellent talk in two parts. We've got a few questions on the chat and a couple of comments. So, Peter, we'll come back to your comments after we address the 3 or 4 questions that we have there already. Alvise.
So the first question we have is from Jim Pizzuto. He asks, when you predict aggradation of the bed, where does the sediment come from? Are you supplying sediment to the model from upstream, or is it the sediment deposited from localized erosion, such as bank erosion, within the ridge? If you aren't supply sediment for upstream, why not? And also, do you allow sediment to be deposited on the banks? This could be an important mode of channel width adjustment in addition to erosion.
Yes, thanks, Jim. Great questions. Let me make sure I get to them all. Yes, we are supplying sediment from upstream, so it's fairly standard approach. We're prescribing a discharge and a sediment supply. And so all of the sediment that's piling up on the bed when we do see that is coming from upstream. There's a simplifying assumption in the mass balance that anything eroded locally goes into that flux out. Your point is well taken, though. That doesn't have to be true, right? I do think in response to some of these restoration interventions, we do in fact see bank failure just upstream of the structure piling up sediment right there. Your other question, oh, I'm sorry, it just flew my mind. What was the second part of Jim's question?
Do you allow sediment to be deposited on the banks? This could be an important mode of channel width adjustment.
Yes, we do, and it is. And that is, we have, for example, simulations where we observe channel narrowing due to deposition on the banks. And, we've struggled a little bit with that because, bank deposition is a little harder to conceptualize than bed deposition, but we do allow that, and bed narrowing through bank deposition can occur when conditions are right.
All right, so I'll combine the next 2 questions. I think they're related. So the first one is, have you looked at different sediment lithology, like different grain sizes, densities? Does that impact your results? And the next one, along the same lines, does your model account for differences in erodibility of the elements? How could that influence timescales and magnitude of the changes?
Yes, so great questions again. Yeah, the primary way that grain size comes in is through the sediment bedload flux law. There's a D50 in there. And so, predictably, as you sort of turn that up, it becomes harder to transport sediment. So we do kind of incorporate that. We haven't explored that in great detail, but it is there. And for the other piece, we do consider the erodibility of the bed and the banks. What we have not done is allowed the roughness elements themselves to change in any way. So we, for example, aren't allowing like a log jam to break up and move downstream. So if you're referring to the erodibility of the substrate, the bed and banks, yes, we've put a lot of work in the manuscript that'll hopefully be out soon into kind of quantifying those effects. But we have not thought about the erodibility or dynamical changes in the state of roughness itself.
All right. We do have another question from the chat. Do you find that slow evolving avulsions persist longer than fast evolving ones? This could influence how you resolve the desire of restoration to see quick changes versus you observe time lagged responses.
Yeah, we do. So generally, there are 2 timescales that you're playing with here. The timescale of kind of expanding a channel, or the erosional timescale, is very short, or it can be very short. The timescale of channel infilling, and so the closing off of a formerly active channel, is almost always a lot slower because it usually integrally depends on the generation of roughness through vegetation establishment. Beaver can sort of short circuit that, so I'm going to leave beaver out of this for now. They're very confusing, to be honest. But yeah, slow evolving avulsions tend to persist longer, and we actually have documentation in our data set of avulsions that are slowly ongoing in certain hydrologic regimes and certain sedimentologic regimes for upwards of 80, 90 years, which is kind of pushing the limit of the historical record that we have. These faster evolving avulsions can, yeah, I mean, they can form and kind of revert to a single threaded channel in a matter of a few years. We have very, very few of those in this data set. And I think that speaks to a degree to the fact that we tend to notice avulsions when they're very fast, and we don't tend to pay a lot of attention to them when they're sort of setting themselves up. But most of those perceived fast avulsions are actually setting themselves up over a long period of time, possibly multiple years and multiple floods.
So, Peter, do you want to unmute and share your comments, or we can read them?
Sure. I find it interesting that a lot of earlier work on avulsions focused exclusively on sediment and hydraulics and morphodynamics. And your work focuses largely on macro roughness. And so, the role of diversion angle on building bars, selective deposition. It seems like it would be useful to bring these two threads together.
Yeah, I don't know, Charlie, if you want to add to that too, but I totally agree, and that's part of what we're trying to do. It's I would say kind of easier to do that empirically, where we are looking at the interaction between something like incidence angle and how incidence angle is changed perhaps by wood racking up at the inlet or the bar apex of these bifurcations. There are direct feedbacks between upstream channel direction, the accumulation of wood, and how that wood then changes inflow hydraulics to each channel that we're looking at. It's I think it's kind of, yeah, so it's easier to look at that stuff statistically because we can just go out and look at it and document it. The challenge, I think, is integrating those field observations with the numerical model that we're kind of putting together to look at these paired channels, and especially looking at the interaction between these influences on hydraulics and especially sediment intake to each channel at the inlet versus stuff going on further downstream in each channel. But yeah, that's definitely the way we're trying to progress with this.
That was great, Dan. I don't really have anything to add. Thanks.
All right, and then I guess the first part of Peter's comment was on the rates of sediment supply driving timescales. Do you see that in the model?
Yes, absolutely. It's sort of, part of the reason we don't emphasize it or didn't emphasize it in the talk is a lot of this model behavior, because it's built of components that are quite well understood. Just sort of gives you standard like lanes balance type behavior with timescales modulated by sediment supply rate or the ratio of water and sediment supply. So one sort of encouraging thing is that we see a lot of very standard behavior, including modulation of evolution timescales by water and sediment supply.
Well, I throw in one of my own. I don't see any more questions in the chat. What about systems where there's no, sediment, trees? Think of pure meltwater on ice. Do you just have, like the typical avulsion that follows the big channel high slope? Is that the main answer to that?
I would say weirdly, we still don't. And I think there's a lot of documentation that actually, obviously the background of your like Zoom background really neatly illustrates this.
Those are
Someone,
tidal though, right?
yeah,
That's
well,
right.
yeah, so that might be more title, but agnostically looking at that, we could imagine it's in a landscape with no sediment or wood or something. We still see tightly sinuous channels. And so I think a lot of what Charlie was talking about is that there is a huge influence on how frequently and how I would say energetically flow can get overbank. and transfer between meander bends essentially to basically connect them or not. Someone pointed this out to me the other day, which is it might have been you, Charlie, actually, that if we had purely slope controlled avulsions, we wouldn't have sinuous rivers. We would never get tightly sinuous meander bends that kind of curl back on each other. If flow could get over bank and go between those two, they would always cut off. And you see that even in like ice streams, you see meandering, you see changes in flow direction, and you see bifurcations, which I don't fully understand in those systems. I have a much easier time when I can just reach to wood and be like, ah, it's wood, that's messing things up. That's why it's that way. Um, but those systems may simply be influenced by how frequently and how long a duration flow can get over bank, and then simply upstream changes in flow direction. And you can have, based on the frequency of changes in the direction of channel migration upstream of a point, you can generate bifurcations simply through that mechanism by channels migrating very quickly in one spot and not as quickly just downstream. And that implies to me that we can have these bifurcated systems with just pure water flow flowing over an erodible boundary that contains practically no sediment. That still kind of blows my mind, but yeah.
Just another question that came in, Alvise.
Oh, yeah. So the question is, levee setback reduces flow concentration. Does it increase the probability of avulsion? Is this scale dependent?
Oh, that's a really good question. Not always. And I can point you to some examples, Alex, about actually on the Tolt River too, where yeah, you can set back levees as far as you want, even on something like an alluvial fan. If you have nothing driving water into the floodplain, if water is just perfectly happy to follow a straight channel, it could stay in that straight channel effectively permanently. There's no perturbation to start the process of meandering. I think when we're talking about levee setback, we are really starting from an initial condition in a lot of cases where the channel is very simplified, very straight, and has no mechanism to just break out of that. That being said, in a lot of systems where we set back levees where the system was not as initially constrained by those levees, wasn't straightened, wasn't dredged out, yeah, it absolutely does increase the probability of an avulsion. I think the salient point that we've been finding in our field data set is that avulsion is much more typically partial and slow rather than full. And I think that's been a lot of the hesitancy that has kind of caused people to be very kind of afraid of setting back levees in places that they think the river's going to suddenly jump way across the floodplain. And I think as humans, we are a little scared of full avulsions. I would encourage us not to be. We can manage them just fine. But what we're finding in this field data set, at least, is that they're just not common in most river systems. If you can supply it with a little bit of wood, if you're doing a levee setback, if you can allow the river to move a little bit upstream to change its upstream incoming flow direction every few years, that can be plenty to prevent a full avulsion and prevent this kind of a little bit scarier scenario that people might be worried about. As for whether it's scale dependent, could you clarify that, like spatial scale dependent or?
I'm contrasting the scale of the Tolt with the scale of the Nooksack.
Oh, yeah. I don't think so, actually. I don't think it is like Riverside. Yeah, like Riverside, I don't think that actually plays a huge role on those scales, because those are both rivers where the channels can get much larger than wood jams can kind of fully obstruct the main stem. Where it might be important, and gosh, I thought this would pop out in that empirical data set. I thought I'd be talking about this, and it just hasn't yet, which is confusing me. Really small channels where wood can much more easily block the main stem, I would think that those should have different response dynamics, and they just don't. I'm not seeing that yet. That may be due to the limited field data set. I don't understand it. If you want to talk through that, that's getting me right now. It should be scale
Yeah,
dependent.
I was going to ask whether there was a tree length scale that emerges.
Yeah, there should be, and it's like I mean a lot of the research on wood mobility, we've talked about like the length of trees relative to the size of the width of channels or the diameter of trees relative to the depth of channels. Those things pop out as like not nearly as clear-cut controls as we would think they would be. wood pivots, wood bounces along the bed. Sometimes it floats in the overbank. Yeah, those aren't coming out yet as clear-cut kind of scale-dependent thresholds. Although they really should. I don't understand why not. So, yeah.
Thanks.
All right. I don't see any more questions in the chat. So, and I also think our time is kind of up. So with this, I would like to thank Dan and Charlie for this super interesting talk they had today. And thanks to everyone who joined us today. We had a great audience, for real. We will see you next month on March 11, and we will be hosting Mirko Musa from EPFL in Switzerland. We will share more details via mailing list and social media, so you should keep an eye on them. And we'll see you on March.
All right. Thank you all. Thank you, Dan. Thank you, Charlie.
Thanks, everyone.
Thanks, everyone.